Let H be a Hilbert space and T from H to H be a linear transformation which satisfies the symmetry condition Tx y, the inner product, is equals to the inner product of x comma ty for all xy belonging to H. Now it follows that T is continuous and therefore self-adjoint. So before I had a continuous operator while defining self-adjoint. So the way I defined self-adjoint was as follows. I took a continuous operator, and if that operator satisfies this condition here, then it is self-adjoint. I said if it satisfies this for all x, y belonging to capital H, then T is self-adjoint. And now what I'm saying here is that if you have just this, which is purely algebraic thing, then T must have been continuous the whole time. So the way we do it is we show that T is closed, and then the result follows from the closed graph theorem. So in order to show that T is closed, what we do is we take a sequence xn in H, and we take a convergent sequence with limit x, and suppose that Txn belongs to H and it converges to Y. So what we have are two things. We have Txn converging to Y and Xn converging to X, and both Y and X may be read like this. So both Y and X belong in my space H. So everything basically belongs in H. So what I do is, what I want to show is that if this is the case, then Y is equals to Tx. So the way I show it is I take the inner product of Y minus Tx with itself, and then I replace the definition of Y with its definition. So Y is defined like this. See that Txn converges to Y. So now I do a series of trickeries. I take T outside in this step, and then I take T to the other side. Since this was given in this step, and then I take the limit inside, and it gives me 0. Thus, I can show that Y is equals to T of X. So that was the Hellinger-Toeplitz theorem. The next thing that I do is I show that I show a remark. It goes as follows. Let H be a Hilbert space and T be a self-adjoint operator. It follows that Txx, the inner product, is always real. Hence, the complex conjugate of Txx is equals to xdx, and because of the inner product property, it becomes out to be this. So it follows very trivially. The complex conjugate of AB is PA, and since the AB, PA, and because of the self-adjoint stuff, it goes this way. So if A complex conjugate equals to A, then A must be real. So Tx comma X is always real. Which brings us to our lemma. We have H, which is a Hilbert space, and T be a self-adjoint operator, as follows that the norm of T is equals to sup norm of X equals to 1, the mod of inner product Tx comma X. So the way we prove it is as follows. We define this quantity here. Let me choose a good pencil to do this stuff. So we define this stuff here to be my M, and then I use Cauchy-Schwarz inequality to estimate it like this, and I have norm of X equals to 1, so I have equals to norm of T. So in this way, M is less than equals to norm of T. Now it might be a bit difficult to see with all these things that I have done, but okay, let's try to see this way. So what I have is I have the inner product of T x plus y comma x plus y, and then minus T x minus y comma x minus y. So I just expand everything. I expand everything and I get this quantity. If you just expand everything out and multiply everything out, it will be this. Now this to this is again the complex conjugate of AB is BA, and interestingly this to this is because T is self-adjoint, so it brings the T over this side, and now I have 2 times of inner product of Tx comma y plus 2 times of complex conjugate of inner product of inner product of tx comma y, therefore I have 4 times of real product of tx comma y. And now from this, it follows that this is true. Why does it follows from this? So norm of tx plus y comma x plus y. So if I have an inner product, I take the norm of it, then suppose if I have this quantity. Okay, I start with this one. So I have this one here defined, and what I can do is I can take norm of x plus y outside, and then this becomes this. So start with here, we start with here, and then if this thing here is exactly equal to this thing here, but if I take the norm of z outside, then I can write t of z comma z inner product whole norm. I do not need to have the condition that norm of z should be equal to 1, because then it would be less than equal to norm of z square m, because of this. If you have a problem in understanding this, I really cannot help you. I'm just kidding. It's really difficult to understand. It took me a whole while to understand this stuff. Come on, let's look at this way. So if you have dz comma z, you have the inner product. Now what you should do is norm of z is not equals to 1. Okay, so you take t and you start from this case. If I have this, then the norm of this complete quantity here is equals to 1. And okay, but now see this, supremum of this quantity, I defined it to be m. Okay, so the sup of this I said is m. So the supremum of this is m. So let me say that it's always less than equals to its supremum. And then the next thing that you do is you take the norm of z outside and you multiply it there. That's exactly what we have done here. It's exactly what we have done here. There's no other thing involved here. Anyway, so now what we have is this, and from this, if you look at this, so the way you estimate this is, so this thing here, I do the triangle inequality and I say that 4 retxy should be less than this thing mod of this complete thing plus mod of this complete thing. That's what all I have written here, and I have estimated these two quantities here with my mx plus y and mx minus y, and that's why I have written it like this here. And I multiply the whole thing out, add them all out, or I just use parallelogram identity and I get this. And from this I cut 2 and 2, so it becomes 2 on this side, and then norm of x square plus norm of y square is itself equals to 2, because norm of x and norm of y are 1. And finally I get this thing, and I know that the real part of tx comma y is equals to tx comma y, because, well, if I substitute rather than y, if I substitute tx by norm of tx, so it becomes the dot product. Oh, sorry, let me write it down, or maybe I've written it down here. So yeah, it's here. So if I just replace y by, if I replace y by this quantity here, then this becomes simply the norm of tx square. Then it gets cancelled, and the norm is, since norm is always real, so this is equals to the norm of tx. So what I have essentially is that the real part of this is given by norm of t, and thus I can say that norm of t is less than equal to m, and hence we have the result. Now the next thing that we're going to see is that let H be a Hilbert space, and let P be an orthogonal projection if and only if it's idempotent and self-adjoint. So it's just a proposition that P is an orthogonal projection if and only if it is idempotent, and self-adjoint. So that's just a proposition, and the next remark we see that the eigenvalues are all real because if you see from the computation we have Tx equals to lambda x. So norm of x square can be written like this. I put the lambda inside, then lambda x equals to Tx. I put the T over that side. It's only true for if T is a self-adjoint operator. And Tx equals to lambda x, I put the lambda outside, then if lambda equals to lambda complex conjugate, then lambda must be real. So all eigenvalues, if T is a self-adjoint operator, are real. Now we show that all spectral values of T are also real. So this is a basic argument. The way we go through this argument is, okay, let's go as follows. So let H be a complex Hilbert space and let T be a self-adjoint operator. Complex number lambda lies in the resolvent set rho T if and only if there exists a constant C greater than 0 with this property that norm of lambda I minus Tx is greater than or equal to C times norm of x for all values of x belonging to my Hilbert space H. So what does it mean to belong to a resolvent set? Belonging to a resolvent set means that lambda belongs to a set of complex numbers such that lambda I minus t belongs to LHH, that is the set of all bounded functions, and it exists and is continuous. So the basic idea of this lemma is that if lambda is in a resolvent set, then this condition holds. And if this condition holds, then lambda is in the resolvent set. So let's prove it this way. So we consider that lambda is in our resolvent set. Now it follows from I equals to r lambda lambda I minus t that, well, of course, if it's in the resolvent set, then r lambda exists. What is r lambda? Lambda I minus t inverse. So if it exists, then okay, I is equals to this thing can be defined. I write norm of x like this. Why? Because this whole thing is I, and I times x is just x. I use Cauchy shorts to split it into two parts. And then I can say that, okay, my C is the inverse of the norm of r lambda, as you can see in this case. C times norm of x is indeed less than lambda I minus tx. Now we go the other way around. We suppose that star holds. And when we suppose the star holds, we have to show that lambda is in the resolvent set. So what do we need to show that lambda is in the resolvent set? We need to show that lambda is injective, lambda is surjective, and so let's see how we would prove that. So the way we go forward with it is we claim that lambda I minus t is injective. Now it follows from star. Let me write it down using a different color pen. So what is star? Star is lambda I minus t x greater than or equals to c times norm of x. So it says that it follows from star that lambda I minus tx is equals to 0 implies x equals to 0. Why does it follows from this? So the question before the house is, why does this follows from this? The reason is simple. So if lambda I minus t x is 0, which means this is greater than or equals to c times norm of x, where c is greater than 0, which implies, of course, that x is equals to 0. So we find out that if this condition holds, then lambda I minus tx is equals to 0 implies that x equals to 0, which implies that the kernel of lambda I minus t is equals to 0. And we know that if the kernel of an operator is 0, then the operator is injective. And therefore, lambda is not an eigenvalue of t. Okay, Now, how does it prove that lambda is not an eigenvalue of t if lambda I minus t is injective? Because if we go back and look at the definitions that we did when we did spectral theory, we would see that lambda is not an eigenvalue if lambda I minus t is injective. Okay, next we show that the image of lambda I minus t perp is equals to 0. Why do we want to show that? We want to show that because we want to show that image of lambda I minus t is dense in H. If we can show that, then we can show that, okay, first we show that the image of lambda I minus t closure is equals to H, and then we show that if the image is dense in the set and it's a closed subspace of the set, then it's the whole set itself. So what we show is we take that let y be a point in image of lambda I minus t perp. Then we do the usual dot inner product trick. We take this element in image of lambda I minus t, and we take inner product of y. We shift this operator to this side, and we say that, okay, ty equals to lambda bar y, and therefore lambda bar is an eigenvalue of t, so that lambda bar equals to lambda. Well, why? Because we just did above that eigenvalues of self-adjoint operators are real. See? Okay. So now we have however established that lambda is not an eigenvalue of t. How have we established it? Just here. Just here we have established that the lambda I minus t is injective, hence lambda is not an eigenvalue of t.
So finally we show that the image of lambda I minus t is a closed subspace of H. Why do we want to show that? Well, till now we have shown that image of lambda I minus t is dense in H. And now if we can show that it is a closed subspace of H, then if you are dense in a space and you are closed, then you are the whole space itself. So I have to prove that this space is closed. How would I do that? I would start by taking a convergence sequence with a limit y in H. So lambda I minus t x is xn is how a sequence in this set would look like, and let's say that it has a limit h. So lambda limit n tending to infinity, lambda I minus t xn equals to y, and it follows from star that if I just substitute rather than x xn minus xm, then I'll get this condition, and from this condition I can see that lambda I minus t xn is a convergence sequence, so it's a Cauchy sequence. Therefore this xn and xm is itself a Cauchy sequence, and since we are in a Banach space, H is a Banach space, then these Cauchy sequences converges, and the point to that it converges lies in the set itself, and thus I can say that xn is a convergence sequence, and we denote its limit by x. So I can say that xn goes to x, and the continuity of lambda I minus t implies that lambda I minus t xn goes to lambda I minus t x for n tending to infinity. This is also pretty obvious that we can say. And now we see that lambda I minus t xn goes to this, and I also said earlier that lambda I minus t xn goes to y. So lambda I minus tx must be equals to y because of uniqueness of limits, and I can thus say that since y is of this form, lambda I minus tx, therefore it belongs in this space. Well, this is just the projection theorem, and from the projection theorem I can see that since this is 0, therefore h equals to image of lambda I minus t. It is because we have proved that this was 0, and we have proved that this is closed, so h is equals to the whole space itself, and thus I can say that lambda I minus t is surjective. Well, if the image is equal to the whole of space, then it is of course surjective, and it follows from the inverse mapping theorem that lambda equals to rho t. So the bounded inverse mapping theorem essentially says that let x and y be Banach spaces, and t be a bounded linear bijection. Then I say that t inverse y2x is bounded, And since it is bounded, therefore rho lambda belongs to rho t. In this theorem, I proved that let H be a complex Hilbert space and T be a self-adjoint operator. Continuous. As continuous self-adjoint operator, it follows that sigma T is a subset of R. So I start by taking lambda in the complex plane that the imaginary part of lambda is not equals to 0. So I know that my complex plane is composed of the resolvent set and the spectrum. So rather than plus, let me write it as a union. So what I do is, once I take imaginary part of lambda not equals to 0, well, I just make use of this identity, a minus a bar equals to 2i imaginary part of a, and I take a as the dot product or the inner product of lambda I minus tx comma x. So I write this as a. So a minus a complement, if you rearrange it, that is complement of a comma b equals to b comma a. So I would write that as, yeah, I just take it to the other side and then I use the self-adjoint property and I would get this equation here. And then I can say that a minus a complement is equals to 2i imaginary part of a, so the left hand side. And if I just multiply all the brackets, I would get the right hand side. And I cut 2i on both the sides, so if you look carefully, it looks like this. So I get this 2i on both the sides and I cancel them, and then I estimate this quantity. So I take a mod of it and then I estimate it by this. So I just write this as less than this, which makes complete sense because it is equals to the imaginary part of the inner product of lambda I minus tx comma x. So it should be greater than the mod of the whole of inner product of lambda I minus tx comma x, which is less than equals to this using Cauchy-Schwarz. And then I can invoke the star condition that I had before, that if lambda belongs to the resolvent set, if and only if there exists a c greater than 0 such that norm of lambda I minus tx is greater than or equal to c times norm of x, and I have hence proven that lambda belongs to the resolvent set. So I know that since lambda belongs to the resolvent set, so I started with taking a lambda in the complex plane such that imaginary part of lambda is not equal to 0, and I showed that if the imaginary part of lambda is not equal to 0, so I say that take lambda not belonging to R, that is the imaginary part of lambda is not equals to 0. So this implies that lambda belongs to the resolvent set. That is, lambda does not belong to the spectrum. That is, now you can just by using logic say that lambda belongs to spectrum implies that, rather than that is I can write implication also. So lambda belongs to spectrum implies that lambda belongs to the set of real numbers. So let me repeat this argument again. So I took a lambda which does not belong to R, and I show that it implies that lambda belongs to the resolvent, which is the same as saying that lambda does not belong to the spectrum. So lambda not in R implies that lambda is not in the spectrum. And the counterpositive of this argument is, so let me write it, lambda does not belong to R implies that lambda does not belong to the spectrum. Now a counterpositive of this argument is that lambda belong to the spectrum implies that lambda belongs to R. This is all I showed here. And in the next argument, in the next theorem, I show that let H be a complex Hilbert space and T be a self-adjoint operator which is continuous, and it follows that the spectrum of T, well, before moving on from there, I want to just add one last thing to this theorem, and that is that spectrum is a subset of R, not the whole of R, because I just showed that if imaginary part of lambda is not equals to 0, then lambda is in the resolvent. But I did not say that the resolvent consists only of those lambdas whose imaginary part of lambda is not equals to 0. So the implication is from here to here, not from here to here. It could be the case such that lambda belongs to the resolvent and lambda is a number on the real number line, because when I mentioned that the complex plane is the union of these two sets, so these two are the sets of points. So resolvent is a set of points and the union, the spectrum, is a set of points. So I just showed that there is no way that the spectrum can lie here. There is no way at all that the spectrum, so all the possibilities for the spectrum to lie are here. But at the same time, I did not say that the resolvent cannot lie here. I'm saying that this is all values here are in the resolvent, and I'm saying that the values of sigma are all here. It might not be all of R, so there might be other values which belongs to the resolvent which might lie on this line. So that's why I'm saying that the spectrum is a subset of R. And okay, next, going to the next theorem. So I have a self adjoint operator and I have a complex Hilbert space, and I'm showing that the spectrum of T is a subset of M to capital M, and M is defined like this and capital M is defined like this. So to be explicit, I can say that small m is the infimum of inner product of Tx comma x, such that norm of x equals to 1, and capital M is the supremum of the inner product of Tx comma x, such that norm of x is equals to 1. And now I'm saying that furthermore, small m and capital M are spectral values of T. So I would just keep this theorem on a halt as of now, and I'll come back to this theorem later. But as of now, I just want you to remember the statement of the theorem such that the spectrum is a subset of small m and capital M, and such that small m and capital M are both spectral values. And immediately after that, we follow a corollary, and it essentially says that let H be a complex Hilbert space and T be a continuous operator which is self-adjoint, and it follows that the norm of T is given by R of T, where R of T is the spectral radius, which is the maximum of all the spectral values. So essentially I said that it was the supremum of all spectral values, but since the spectral set is compact, then the supremum is attained, so it's the maximum of all spectral values. And in the notation above the above theorem, so initially in the theorem above I say that sigma T is a subset of small m and capital M. And now I say that, okay, let's start from here. So I know that norm of T is defined like this, and now depending whether small m and capital M are both positive or both negative, the norm of T would change as follows. So if you remember above, that if this quantity here is more negative than this quantity here is positive, then if I put the modulus on this, then the norm of T would be given by this small m. And similarly, if this is negative and this is positive, but this is more positive than it is negative, suppose this is -2 and this is +10, then of course the norm of t would be given by capital M. And that's all I'm saying. The essential idea is, since the norm of t is defined as the mod of the inner product of tx comma x, and the small m and capital M are defined without the mod, so depending upon which one is greater, so depending upon the modulus of which one is bigger, I would assign that to be my spectral radius. So that's the essential idea behind this. So here I say that the norm of t is equals to the max of this, because yeah, I mentioned and the next point is the r of t is the max of the mod of the spectral values, and hence I can say that in the case of self-adjoint operators in Hilbert space which are continuous, I can say that the norm of t is given by the max of mod of m and mod of capital M, and it is equal to the spectral radius. So let H be a complex Hilbert space and T be a bounded linear operator from H to H, and T is self-adjoint. Now it follows that the residual spectrum of T is null. What do I mean by the residual spectrum of T? I mean the set of all values of lambda such that lambda I minus T is injective, not surjective, and image of lambda I minus T is not dense in X, which means that the closure of the image of lambda I minus T is not equals to X. And how do I proceed? I proceed by showing that I take a lambda belonging to real number. Why real number? Because all spectral values of bounded operators, self-adjoint bounded operators, are real. Now we show that image of lambda I minus T is not a dense subset of H. So if image of lambda I minus T is not a dense subset of H, so if this condition holds, then I prove that lambda belongs to the point spectrum. And what was point spectrum? Point spectrum was the set of all values of lambda such that lambda I minus T is not injective, and it was. Therefore, those values of lambda were eigenvalues and so on. So according to projection theorem, I can write my Hilbert space H as a direct sum of a closed subspace of H and the perp of that space. So since image of lambda I minus T, I do not know whether it's closed or not, so I close it and I take a direct sum with the perp of it. And if image of lambda I minus T is not dense in H, then there exists a Y, so I can write it there exists a Y belonging to image of lambda I minus T perp such that this condition holds. Why? Because these two spaces are orthogonal to each other. So, and if you take any two elements in them, the inner product would be 0. So this is for all x belong to H. Since T is self-adjoint, I can take it this side and I can write this for all x belonging to H. But here I see that this implies that Ty equals to lambda y, so that y is an eigenvector of T with eigenvalue lambda, and hence lambda belongs to the point spectrum, and thus I can say that the residual spectrum of T is null.
So the next thing that we're going to do is just we're going to do functional calculus for self-adjoint operators. So what do I mean by functional calculus? So let H be a complex Hilbert space and T be a self-adjoint operator and P be a polynomial. So it follows that P of T is equals to the sup of norm of P of lambda, where lambda belongs to my spectral set. So you have a function applied on a set. Okay. So you take all the values of lambda belonging to your spectrum of T and you take P of lambda, mod it, and that is your norm of P of T. So one thing I want to prove is that if my operator T is self-adjoint, then P star T equals to P complex conjugate T, because, well, And the simplest way to show it is as follows, that if I take ptx comma y in a product, it is equals to x comma pt star y, and then pt star can be written like this, and I have seen from an identity above that s plus t star is equals to s star plus t star. So I can multiply all these stars inside, but since t star equals to t, so it remains t. But on the other hand, I have also seen an identity that alpha t star is equals to alpha bar t star, but t star equals to t, so it just becomes alpha bar. So everything becomes complex conjugate, and hence I can say that the complex conjugate, so p complex conjugate t equals to p star t. And now note that T star PT is self-adjoint because S star is always self-adjoint. It's a very trivial argument. We can find it always true. And now I can say that PT star PT equals to complex conjugate of PT times PT. And now I do a series of calculations. So this is nothing but the norm of this thing. Okay, we have seen it multiple times. Okay, norm of t equals to sup norm t of x, norm of x equals to 1. And square on both sides. Now I can write this thing as this, no problem, in this also. And now I can bring p to the other side. I can write it p star t. Then p t star is, well, this is mod of norm of t of x comma x, which is equals to norm of t of x. We saw this definition above, and we saw it for t to be a self-adjoint operator. The norm can be given like this, if you remember it. See, that norm of t equals to sup norm of tx comma x, which is exactly what's written here. Now here I can see that, okay, this is equals to the supremum of lambda such that lambda belongs to this. Well, I've seen this also before, that the norm of p of t, if you can see from above, that, well, norm of p of t is equals to sup norm p of lambda. Lambda belongs to sigma of t. But I've seen something before that also. I've seen that, well, in the self-adjoint operator, norm of t equals to the spectral radius. So p star p is a self-adjoint operator, and then the norm would be equal to the maximum of the spectral value, which is exactly what's written here, of course. And now I can say that, okay, I can replace pt star by p complex conjugate t, and then I can make use of my spectral mapping theorem. So spectral mapping theorem says that p of sigma of s equals to sigma of p of s. So what it essentially says, that here is a set x, so p of x is p of x for all value of x belonging to capital X. So it's essentially saying that this is also giving me a set. So basically it's an equivalence of set. You have to see it that way. So, well, I can say that p bar lambda, p lambda for all lambda belonging to spectrum of t is the same set as lambda for lambda belonging to spectrum of p bar t pt. Well, this is something very deep, and you need to go really deep in order to understand that. No, I'm just kidding. It's super simple stuff. Now look at this. So what we have, p, my polynomial. So this together is a polynomial, p bar lambda, p lambda. Okay. What I'm saying is that the spectral value of p of s, so s is the operator, you have to keep that in mind. So the spectral value of p of s is equals to p times, if you take p, and you put all the spectral values inside of this. So P lambda for all lambda belonging to sigma of t. So it would make more sense if I replace this S by T, so that would confuse you a bit less. P of sigma T equals to sigma P of T, because this would give me a set. This will also give me a set, the set of all spectral values of PT, the set of all. So P of X is P of small x for every value of X belongs to capital X. These are two sets which are equivalent. The spectral mapping theorem tells me that. I do not have the time to go through the proof of it, but it's true. So, okay, so from here to here, I am taken by the spectral mapping theorem. And, this is just the norm of P lambda square. And I take square outside, so it's exactly equal to this. So what I have proven now is that norm of P of T equals to the sup of norm of P of lambda for all lambda belonging to spectral values of T. Now I have the Stone-Weierstrass approximation theorem, which basically tells me that polynomials are dense in the space of continuous functions. Now I start with a Hilbert space, a complex Hilbert space, and I have T as my self-adjoint operator and F be a function in CMM. Now we define f of t is equals to limit n tending to infinity Pn of t, where this limit is taken pointwise. Okay, pointwise just mean f of t of x equals to limit n tending to infinity P n t of x. Now, as any good mathematician, when you see this definition, two questions must come into your mind. The first question is, why does P and T converge? Why does this converge to this value? The second is, what if I take two different sequences? One is Pn and one is Qn, and both of them converge to f. Then should f of t be independent of the specific choice of Pn? Because I can have many number or many sequence of polynomials which converge to the same f of t. So what I do is I say that, okay, P and T is convergent sequence in LH, since, why is it convergent? Well, if you see this, it is nothing like this. It's just the definition we saw from above. And, well, this equals to the supremum of this. And you look at these two things. Lambda is a subset of m comma m, or should I rather say that sigma t is a subset of m comma m, so the supremum would only increase. See? And now the supremum here is nothing but the infinity norm. Okay, now I know that Pn and Pm were Cauchy sequences. Well, they're convergent sequence. I define above that Pn is a sequence of polynomials such that limit of Pn minus f in supremum norm is equals to 0, which means that in the supremum norm this is convergent sequence and this is Cauchy sequence. Hence this is a Cauchy sequence, and since we are operating in a Banach space, the Cauchy sequence converge. So indeed, well, all it shows me here is P and T is a convergent sequence, because this is bounded by this and we are in a Banach space, so these convergent sequence must converge to a point. Now the second, we show that the limit is independent of the choice of approximating sequence Pn. Now suppose that I have two different sequences, Pn1 and Pn2 of the polynomials, which converge uniformly to f over m comma capital M. Then I define two limits, Pn1t and Pn2t by f1 and f2. And then I approximate f. I say that we find that I just use the triangle inequality. I just add Pn1t here and add and subtract here. And I say that, okay, this tends to 0 because of this. This tends to 0 because of this. But this, you see, also tends to 0 because Pn tends to f. So now what I have is if I take n tending to infinity on both the sides, well, this tends to 0. So this must be 0. So fn must be equals to f of 2. So that's the two things. And in the last case today, we would just prove that let H be a complex Hilbert space, T be a self-adjoint operator, and I have to show these three results. So what we do is I know that the results are true for polynomials. Okay, if I just substitute f and g to be polynomials, I know that the results are true. But when I do that and I take limit on both the sides, then they would be true for continuous functions also, because polynomials are dense in the space of continuous functions. Furthermore, f of t commutes with every operator s belonging to H, which commutes with t. And S does not have to be self-adjoint. So, well, now he says that the identities 1 to 3 are obviously correct for polynomials and therefore also for uniform limits of polynomials. Now, we take a sequence of polynomials which converge uniformly over to f over m comma capital M. Now, this is simply the definition. We just saw this definition above. Okay. Now, I take the limit outside because continuity of the norm. Well, now what I do is that I saw a theorem above and a theorem on page number 85. So let's go to page number 85. So my theorem says that norm of P of t is equals to the sup norm P of lambda, lambda belonging to the resolvent set of t. So sup exactly norm of P of t replace by the supremum exactly as we saw above. Now, since it's uniform convergence, I can swap these sup and lim. Now I take the limit inside, then Pn lambda becomes f lambda, and then we get this result finally. Now, the second thing that I would like to show is that given st equals to ts, I have to show that I show first that s of p of t equals to p of t of s. So if p of t is any polynomial given like this, I take an operator s and I multiply it and it looks like this. Now I know that st equals to ts, so I swap it so it looks like this. So this is what we are doing. We are taking f of t of s. Instead of f of t, I substitute this definition of f of t. Then, well, it's a constant with respect to n, so I take it inside and then I swap the order. I take it outside and limit of p and 10t is simply f of t, so I write f of t.